Recording progress.
All right, guys. So today we have two things that we would like to learn. All right, I'm going to take you back a little bit about, we're going to bring in mathematics. We're going to bring in sinusoidal waves. We're going to bring in a little bit of the algebra and manipulation of trigonometric functions, but not too bad. We still don't have any calculus. That's good. So I think that is still fine. All right. However, what we would like to do today is there are two main stuff. And I think that was the question back in maybe last week or a week before, that is there a way that we can manipulate waves that sort of like come together more than one wave at one particular point in time? Does that make sense? So that means what we are trying to do here is just talking about, so like, hey, when you have more than one waves and then you would like to have them combined, what is the final effect of that? And it turns out, yeah, you can. And it's going to sort of like give you a lot more of the stuff that we can learn. Okay. And actually, when I say more stuff, is complications and complexity start to creep in. But the good thing is we live in the world, or maybe in the universe, that is still the majority of the phenomena that we are looking at is still pretty linear. So you will see what I'm talking about. So the properties of waves that we're going to talk about today is called interference. So now they can interfere. All right. And of course, that is going to interfere with our life a little bit here. Okay. All right. And the underlying principle that we're going to use to describe the waves interference is superposition. This is what we want to do. You want to do superposition of waves, all right? And the concept of this one is going to be super simple in the sense that 1 + 1 is equal to 2. Isn't that cool? So the good thing is, look at this one. If you have wave that can be described by y1, so y1 could be a function that's, everything that it looks like everything that you have learned before. It could be sinusoidal waves. It could be a pulse. It could be anything x plus or minus vt. And then you have another waves coming in, okay? And then it's somehow they're gonna, right now it's on a string, so it's one-dimensional. So you only have two directions to move. It's either left or right. And let's say y1 is moving to your right, y2 is moving to your left, and then eventually they're gonna meet at some point. So question is, what happened when they actually meet? The answer is super simple, guys. You just add them. That's it. Okay. Is that simple? And that's it, guys. That's all the lecture today. That's it. There's nothing else to it. As long as we're dealing with just a linear wave. Once again, we hit this word one more time, linear. So every time it's linear, 1 + 1 is equal to 2. So good thing is most of the stuff that we're going to look at in general system, the waves combination will follow a very super simple principle called superposition principle. And that superposition principle has the characteristic of the linear. We're going to utilize the linear waves. So that means 1 + 1 is equal to 2. And that's it. What happened next? After waves meet, and the resultant wave is just the addition of the two, and the wave will just continue on, just keep going. And that's why they interfere, in the sense that when they meet, they're going to interfere somehow. All right. But now you sort of like have a peace of mind saying that, Ajahn, even though you have more than one wave, but then at the end, all you need to do is just add them all up. That's it, guys. That's the take-home message here. Okay. We are dealing with linear waves, and the combination of waves, just add them all together. However, the stuff that we're going to learn is this. What happened if the wave that coming and meets at the same point? It's just accidentally, or it doesn't have to be an accident, but what happened if somehow the way that they move, they have the opposite displacement vector? See, y1 is actually right now is sort of like moving up. The power is sort of like in a positive displacement. And then the y2 has a negative displacement, and then somehow they meet. Don't care. At the end, you still have y1 + y2 no matter what. You see what I'm saying over here? Okay. So what you have over here is just add them. But because displacement are just pointing in the opposite direction, so that's why, I mean, you just have a little bit of smaller wave when they are combining at this point. But afterward, everything will just keep going. So Y2 will just keep going to the left, Y1 is keep going to the right, and you are done. Cool? Okay. Okay, bye. What does it mean? Your old sound is more clear. Ah, yeah, something is wrong, right? I know, because I think a couple of people complains about it doesn't sound as before. I don't know. I haven't changed anything. That's the weirdest stuff. Okay. All right. I'll try to speak closer. It probably was my computer. Oh, shoot. See? Okay, bye. I mean, you cannot like listen to my voice anymore, right? Oh, not good. Not good. This is not good. I don't know why lately just like things are changing by itself. I haven't touched like all those like whatever at all. Only just move microphone in and out. Okay, so let me try. What can I try? I can lower the master down and increase the, or maybe I can do this. What about this? All right, just reduce the noise here, increase the master. All right. I was talking about when you said this is all the lecture about. Okay, my bad. มุกกระดาษเองไหม? I'm confused. Okay, all right. So does this sound better? Does this sound a little bit better? Okay, I just reduce the gain and just increase the master a little bit. All right, but it's still bearable. All right, it's the same. Oh, shoot. Yes. Oh, my bad. I forgot to plug in the USB. Oh my God. Is this better now? Oh my God. This is best. Best mean I forgot to plug in the USB. I think this is awesome.
Okay.
Oh, it's so clear. Okay, my breathing, maybe it's just a little bit too much then. All right, okay. Oh, was it because of this USB stuff? Oh my God, this is, okay, all right. Wow, all right, thank you for like bear with me for almost 10 minutes here. All right, so is this good now? All right, well, it's just, all right.
Okay.
Give a little bit of like sharing a little bit here, guys. Oh my God. Okay, so let me come back to what we have right now. Okay, so the conclusion that we have was just saying that every time you have more than one waves and they somehow meet at some point, you don't have to worry of anything. You just add them all up. That's it, guys. It's as simple as that. So if you have 2, 3, 4, 5, doesn't matter. It's a summation, but it just depending on the displacement of that particular waves, that it has a chance that you might get the cancellation effect. Does that make sense to you? So when you look on the left case, the displacement is pointing in the same direction. So of course, the end effect of this one, you get a bigger wave while it's combining. But of course, it's not going to stay like this forever because we have already learned that waves never stop moving. So they're going to move apart and that's it. All right. But at the time of the combination, you can say you have a bigger amplitude wave or whatever. But anyway, the point is you get the combination that give you the sort of like you say it's the constructive. You get a bigger displacement. But on the other hand, if the displacement of those two waves are pointing in the opposite direction, I mean, you do the additions just like before is y1 plus y2, but it's just the combination give you the smaller waves at the end. So you can say that this is a destructive combination. So this meeting of more than one waves, we call this interference of waves. All right, they are interfering each other. Okay, and you can classify the way that they are interfering into two main categories. It's either constructive or it's either destructive. All right, the constructive one is you gain a bigger displacement after the summation. The destructive one is you get a smaller one. Cool? All right, that's as simple as this one. Nothing more, nothing less. This is it. Just a simple
superposition principle, 1 plus 1 is equal to 2, 1 minus 1 equal to 0. Simple as that. All right. But the fun things start to happen when you combine this principle to our beloved sinusoidal wave. Yeah? You love it, right? So what we have right here is, what if we have a continuous sinusoidal wave, which, I mean, you love it. I mean, Majan, this is easy. I can describe sinusoidal wave using sinusoidal function. But what you can see over here, even though you see it in blue, but actually there are two waves on top of each other. So what you're saying right here is, it turns out, look on the left, guys. Now you should be able to read. All right, so let's read along with me here. Y1 is this. You got this one? Amplitude is A. K give you the 2 pi over lambda. You get the wavelength. Omega give you the 2 pi f. You get the frequency. You get the velocity by taking the ratio of omega over k. Cool? Everything about waves is on here. Okay, and on the left, the y sub 1 is just the displacement of the medium itself at x and t. Cool. What about y2? What's the difference, guys? Wajan, look at the sign. It's a negative sign, so it means the y1 is a right traveling wave. Same thing with the y2, same amplitude, same wavelength, same frequency, that must be same speed, and it's going in the same direction as well. So the only thing that is going to change between, I mean, it's going to be difference between y1 and y2 is going to be this phi over here. You start to see what is, I mean, now we know how to read waves. It's kind of nice. So what you have in this scenario is, I have two waves, y1 and y2, exact same wavelength, same frequency, same speed, same amplitude, same directional, traveling directions. The only thing that is going to be different is just the phase, that phi right there. Okay, so if I set this one to 0, what happens? This is the first case right here. See, when phi is equal to 0, those two waves are on top of each other. So this is the reason why you get only the blue curve here. It's supposed to be blue and green, but right now you only see one. So that means those two are just on top of each other. But then what is the resultant wave, guys? Well, Ajahn, you just add them. Right? Does that make sense? That's it. So the resultant wave is just y1 plus y2, but at the time that you set this to 0, you're only going to get 2a sine kx minus omega t. See that? And can you read this one? Well, Ajahn, yeah. It's the same wavelength, same frequency. The only thing that is going to be different is just you double the amplitude. And that's the red curve. That's your final wave right there. Isn't that cool? See, simple, yeah? All right, now try one more. If you want to do like acrobatic move, Majan, I want to try something else. Let's take phi to be something more interesting. I'm going to set phi naught to be 180. So what is 180? It just translates your sinusoidal wave by half a cycle. You guys with me? So if you look at the blue, okay, let me zoom in here. If the blue, that's your y1 has no extra phi or anything. So you start from 0, 0, that's the blue. But look at the green. The green is the blue that gets shifted by half a cycle. So if you translate the blue to your right, you get the green. See that? Okay, so that's what it is. It's just half a cycle difference. So, perfect. If you set this phi to be 180 degree, or, I mean, you can think it's a pi. So what you get is the perfect opposite oscillation between the blue and the green. See? They are perfectly out of sync. Opposites. They're oscillating in the opposite direction at all time. And can you expect what should be the final result? Of course, Ajahn. You're going to get nothing. And this is the reason why in the middle, you get a red curve that is just perfectly flat. 0. You get the net 0 wave. See? So when you have a continuous wave, things get more interesting. Because if you go back here, it's just a pulse. So you get some cancellation. So it might be just, go to zero for a fraction of time, and after that, everything just show up one more time. But when you have a continuous wave, things will just continuously cancel each other. So at the end, you get the red curve, means you get nothing. You get zero. Cool? All right, that's what it is. So we call the first case that is a constructive interference, but because they are oscillating in a perfect synchronization, everything is in sync, we call this an in phase. They are oscillating at the same rhythm. Cool? On the other hand, back in the case of the second one, when you have the phase difference of a pi or 180 degree half a cycle, you call it an out of phase because they are perfectly opposite at all time. Cool? You get nothing out of it. All right, nice. And that's what if, well, Ajahn, I want to play around with this phi. I want to try something else. Say 60 degree. What will be the resultant wave? All right, graphically, you can do it. You got the blue, that's your original. And then you shift that blue by 60 degrees. 60 degrees is like 1/6 of a cycle. You get the green. And all you have to do is just add these two together. So what you get is the red as your final waves. And what is it? Now we need a little bit of like trigonometric identity. So let's give it a shot. You guys remember this formula here? Sine A plus sine B equal to 2 cosine the difference over 2 sine the sum over 2, something like that. Back in the day that you did like some trigonometric functions in high school. All right, so we can just add them. So all you have to do is just take the first one, take the second one, add them together, and then you just rewrite it, make it nice. And this is what you get at the end. Following this formula over here, you get factor of 2 here. I pull out a common factor A. You do the cosine of the difference over 2. When you take the difference, the kx minus omega t cancel. You will be left with just phi over 2. And the last term, psi of the sum over 2, just add them together and divide it by 2. You get this portion right here. That's it, guys. See? It's just pure algebra right here. Cool?
Okay.
I can say this is it. This is it. What you have done today is this is in the nutshell, this is it. All right. But in terms of the detail, you have to get used to what the phi is trying to do. Okay. The phi right there will be the parameter that determines what should happen to these two waves. Are they going to be perfectly in phase, out of phase, or somewhere in between? So the phi is the key for you to tell what kind of interference that you're going to get. All right, before we dive into some mathematics today, can you imagine what kind of application that use this type of interference? Something that very close to you, something that you use interference of sound to help you, do something or create something or, just build something. What kind of device or what kind of like stuff that you maybe have used and use these techniques? Anything? Yeah. Oh. Anything that you thought about? It seems like cancellation of waves seems to be very useful here. The answer is, have you used the noise cancelling headphone before? Yeah, that's it, guys. You need that. You need exactly out of phase combination. And the reason that the noise cancelling headphone works is just because if you look at the noise cancelling headphone, it has a microphone built in. So that microphone in that noise cancelling headphone just listen to the ambient noise, and there is a circuit flip that noise 180 degree in phase. And when it recombine with the incoming noise, incoming ambient sound, it's get a cancellation effect and eventually try to get to your ear with almost nothing. So that's why it's quiet. Sounds cool? All right, so that's why the noise cancelling headphone has to listen to the ambient sound all the time. Okay, and back in the day that when the processing power is not so fast, it cannot process like an abrupt change in sound. Like you clap a hand quickly like this. it might still have some leakage coming out. You can still hear a little bit because it might not cancel the wave in time. But because right now the processing power is so fast and everything is so small, everything just squeezed into maybe just inside your earbud or maybe just a tiny piece along your wire. I mean, you hear almost nothing right now. So good. All right. And it's like too good to be, I think it's too dangerous, right? It's so quiet. You cannot hear environmental sounds. And then when you walk on the street and stuff, you don't know even car is kind of like coming to you or there's some bicycle going by, or you don't know anything. So it's kind of not good. So I think the newer devices and all this stuff, they have the options for you to turn on and off or even like adjust the level of noise cancellations. Yeah, it's just, you might still want to hear your environment a little bit, something like that. Cool?
Okay.
I don't know if it's cool or not, but I think it has some application here. I find it very cool. All right. Okay. All right. Now, but what kind of complication will come in, Ajahn? All right. It seems like it's so clear. Actually, just the first half of this lecture only need this one slide, I would say. All right. If I just show you this one slide and that is it, you are done. And then we just go, all right, get something to eat and we'll come back later. But no, there is some complications here because when you do it in reality, but Ajahn, who wants to calculate that phi? Think about it. Like, hey, Ajahn, let's do some experiment in our room. And then eventually, if you do something in our room, and how can you measure the phase? This is not something that you can measure by you take like a ruler, you take some measuring tape or anything. No. All right. Usually you have to attach this one onto something else that can be measured more easily. And this is the case, guys. Take a look at this. All right. This is maybe the only relationship that you need to get you to something that you can calculate quite easily here. Now look at this scenario here. It's actually, this can be done in our maybe physics lab and things. It has some sort of like a real lab that's associated with this kind of experiments, right? This is not like an imaginary scenario or anything. This is real. You have a single speaker. Of course, the speaker will come up with like a single frequency sound. And then somehow you split this sound into two paths, all right? So you have two waves, let's say. You try to generate two waves out of this. The bottom half, you direct the sound in the bottom tube, and eventually the tube will lead you back to the observer's ear. No problem. Now, the upper tube has a little bit of difference. The upper tube, if you can see, the upper portion of this one is adjustable. The reason for you to be, you love the ability to adjust this thing because you want to manipulate how long the upper wave has been traveling before it reaches the observer's ear. Does that make sense? You want to manipulate the waves. But of course, to manipulate the phi, in reality, you just manipulate the distance. Because you guys know, if the distance of the wave traveled a difference, the phase will change along with it. By knowing in your head, but Ajahn, I know every one wavelength that's wave travel, you are going to already move your wave by 2 pi in phase. Does that make sense?
Okay.
This is it. This is the key. You can now convert between the phase and the distance through the wavelength. We already learned this. We already learned this one through definition of the wave number K. All right, we just said every time that you stay away from the wave by one wavelength, the wave has already traveled by one full cycle. And one full cycle in phase or in angle is 2 pi. Okay, so that's it. That's the whole point. Is what you can now measure is just like, hey, Ajahn, you just go and measure how long does the bottom waves travel. Let's call it R1. And let's say the upper waves travel R2 distance. So all you have to do is just take the difference of the distance here. So we call this the path difference. And we use it like a delta R. Okay, so we have a path difference. Okay, and if we know the difference in meter, I can convert that into phi by just using this conversion factor. You guys with me? And here comes the question. I don't know, you guys still, I don't know, have you heard of what บัญญัติไตรยางค์ไหม? Have you heard of this one? For those of you that do the Thai traditional mathematics, yeah? All right. To be honest, I don't even know where this one comes from. บัญญัติไตรอย่าง I don't know who บัญญัติ and why is ไตร mean three. All right, but the way that you set things up is actually is a ratio. It's a taking the ratio or proportion. Okay, so the key is if we do like traditional Thai style is the บัญญัติไตรอย่าง thing. So we say we know that every distance of one lambda you already travel in phase by 2 pi. If the distance that we are looking at is just delta r, the phase will be in the บัญญัติไตรอย่าง style. You take the delta r multiplied by 2 pi divided by lambda. Does that make sense? Okay. But for those of you that do international program and all this stuff, I don't think you have this. I haven't found what is the English translation of this บัญญัติไตรอย่าง thing. I don't know. Maybe it's our trick from whoever created this domestically. Cross multiplication. Oh, is that a word? I don't know. That makes sense. Cross multiplication. Yeah. I love that. Yeah, I'll take it. But there's no like try in this word, so I don't think it's super direct linkage between the two. Oh, but anyway, come back to our case here. So what the point is the reason I say it's just proportion because we know that every one wavelength your phase is already moved by 2 pi. So when I say proportion, it means you just take the delta r divided by lambda. See, this is a proportion. You just want to know how many wavelength you have traveled. That's it. This is a proportion. And then you just multiply by 2 pi. That's what it is. Okay, so that's it. All right, but at the end, you get the same end effects over here. So this is the relationship that we can use to convert between the distance into the phase phi. It's just a factor of 2 pi over lambda. And you are done. When I say you're done means, look at these two cases here. The constructive interference that we were talking about before was just given when the phi is equal to 0, right? However, if you turn the cycle of that wave into one more cycle, nothing's come back. I mean, there's no change. Everything will look exactly the same. Or you can do it 4 pi, or you can do it 6 pi. They all will give you constructive interference. See? But if you want to speak in terms of the delta r, you just take the phi, plug it in here, convert into the delta r. So what you have over here is just every time that the delta r is the multiple of wavelength, you're going to get multiple of 2 pi, and you're going to get constructive interference.
Okay.
Simple. On the other hand, if you want a destructive interference, you need the phi to be pi. That was the first case that we studied. But then you said you can always add 2 pi extra to it. So it means 1 pi, 3 pi, 5 pi, 7 pi. All odd multiple of pi will give you the destructive interference because the wave will look half of cycle difference all the time. So over here, if you plug it back into this expression and convert into delta r, what you're going to get is you're going to get a destructive interference in distance every time that you hit. Okay, this is the same as lambda over 2, 3 lambda over 2, 5 lambda over 2, on and on and on. See that? Over here, I can say it's just lambda, 2 lambda, 3 lambda, on and on. And that's it, guys. This is the two extreme cases. It's perfectly constructive interference, good. The phase difference is a multiple of 2 pi. Or if you talk about in terms of the distance, it's going to be multiple of lambda. On the other hand, if you want a perfect cancellation, the destructive interference, the phase difference has to be the odd multiple of pi. Or if you want to speak in terms of the distance, it has to be the odd multiple of half a wavelength. And that's it. We're done.
Okay.
I say done a lot today, right? It's too much. The reason I say done because, I mean, I would say if I want to summarize what I've been talking for the past half hour here, you have only two things to talk about. First, when you have more than one waves meet at a single point, the overall effect is simple. Just add them. It's a superposition principle. And the second thing is you just have to know to convert between the phase and the distance. And the conversion factor is, you know, every one wavelength is 2 pi. You're done. See? That's simple. That's only 2 messages that I was really want to sort of like give it to you today. All right, but give it a shot. All right, we just have to look at examples for you to be able to see what I am talking about. Let's go for it, guys. Okay, cool. Let's practice, shall we? 2 traveling sinusoidal waves are described by the wave functions below. And I think by this time, you must be very comfortable looking at this wave function. Everyone knows how to read this. A, what is the amplitude of the resultant wave, guys? And part B, they just dig a little bit deeper, just asking what is the frequency of that resultant wave. Okay, let's attack the easy one first. Part A. Well, อาจารย์, even though I don't need anything else except I just know that I just have to add them.
Okay.
If you write this one in the exam and actually you don't want to execute the rest, if you say, hey, the resultant wave is y1 plus y2, I think I have to get like 50% of the marks to you already, because I mean you understand superposition principle, all right? And the other half of those marks, it's just you have to just complete the whole mathematical procedure here. Okay, part A, what you have over here is the net wave function is just going to be simply y1 plus y2. Seriously, simple as that. And you just say, Adan, I can see it, even though I don't want to write it down, but I just for clarity. Okay, I think this is a typo, guys. This is t. It's not tau. Just same t here. Plus 5 sine 4 pi x minus, it looks exactly the same. The only thing is just minus pi over 4. Let me change the 0.25 pi into pi over 4. All right, my writing is a little bad today, guys. Sorry, I'm just writing on a very, very small screen at this point. Okay, cool. So this is what you have over here. And if you refer back to this relationship right there, when you have the sum turned into a product, you just use this trigonometric identity. So no problem. Let's do it. So it's going to be equal to 2. That's from the formula. There is a common factor 5. So I just put in the 5 here. And now it's a cosine of the difference divided by 2. So you just take the cosine. You take the difference of these 2 brackets and then divide it by 2. When you look at this one, all those x and t, the kx minus omega t, will disappear. So what you have left over here is just going to be negative pi over 8. You guys with me here?
Okay.
Okay, the difference over 2. Take the difference of those 2 brackets divided by 2. Now followed by the sine, and then you follow by the sum divided by 2. Okay, so you add them and then divided by 2, you get back the original. So it just 4 pi x minus 12 pi t. But then the last term has to be divided by 2. And that's it.
Okay.
If part A asking you what is the final amplitude, of course the final amplitude will be just whatever, wait for it, whatever comes in front of the sinusoidal function in your wave, correct? With me? And now look at the wave that you have at the end. See, can you see this? It looks exactly the same as before. You still be able to read the k. You still be able to read the omega. You still have the sign in between is a negative, so it's still traveling in the positive x direction. All right, you might have a different phase now at the end, but that's all right. It's still the same waves looking. It still look the same, except whatever come out in the front of this will be the amplitude, correct? So not only the 10 will give you that, you have to combine this with that cosine factor over here. So this whole thing will give you the amplitude of the resultant wave, and you are done.
Okay.
Cool? All right, so you can say that part A the amplitude is just 10 cosine pi over 8. All right, so it's not as high as 10 because we know that if it's perfectly combined, the maximum possible combination is the amplitude of 10. But because right now, the phase difference is just pi over 4, is 45-degree difference. So this is the reason why the amplitude is just not as big as 10. It's 10 with a little bit of, some factor multiply in. So this scenario look almost just like this case, except for that problem, we take phi to be 45-degree. So that's why, the wave will come in between. Okay, all right. That's the amplitude of the resultant wave right there. And part B, Ajan, what is the frequency of the resultant wave? I can see that omega is 12 pi, no change. When the omega is 12 pi, I know it's going to be 2 pi f. So that means f is going to be 6 hertz. And you are done.
Okay.
Easy enough for you guys today. All right. We have negative pi over 8. Yes. And
done in amplitude. So negative.
Exactly right. They are the same. Because the cosine of the negative is the same as the cosine of the positive. Yeah, I didn't mention that, sorry. But same thing. If you're dealing with the sine function, sine of the negative will be the negative of sine. However, when you talk about the amplitude, we just take the positive value anyway. Does that make sense? Because it's an oscillation. So the displacement will go touch the positive side and will touch the negative, positive, negative, positive, negative. So the amplitude is just the value of that biggest displacement possible. So you only take the positive numbers here anyway. Does that help? Okay.
And where do negative pi over 8 come from?
Okay. The negative pi over 8. Look at this. To get to this term, I think I need different color here. I try to minimize using this. What a day. All right, here we go. So this term come from the difference, right? So it's going to be b minus a over 2. Okay, according to if we follow this formula over here. Oh, actually, it could be a minus b or b minus a. They are pretty much the same because it's under the cosine function. So over here, what I did was just taking the bracket here, these two brackets, and just subtracting. Okay, so sorry, and maybe I just follow the whole thing here. One more time. Okay, let me do this. These brackets come from a minus b over 2. Okay, so I take the a. This is a. This is b. Okay. All right, so if I do this in this order, you should get the positive pi over 8. All right, but what I did in my head was just I did b minus a. But anyway, the point is, if you do that, a minus b, you get pi over 4 divided by 2. And then y, you get pi over 8. Does that make sense?
Thank you.
Okay, but my bad. Maybe I just always do the b minus a, so that's why I get a negative one. So sorry. Let me turn this into positive or negative then. Would that help? Oh, this is bad. All right, this is very bad. But anyway, I think you guys get my point that the cosine of positive angle and the cosine of the negative one will give the same exact value. Okay, cool. Thank you for the question. All right, it's just my bad. It's just my ambiguity here. Okay, all right. So this is the straightforward application of superposition principle. So from now on, every time that you have to apply the superposition principle to the interference of waves, just add them together. And if you have a way that can manipulate to make it look a little bit cleaner, just like what we did here, we just do it. But in other cases that you might not have any way to make it any cleaner, just say that's it. Just add them. Cool. All right, try again, guys. This is going to be another problem that looks very real. This is real. We can do this experiment in class, actually. So what you have over here is, now, you have a pair of speaker and places 3 meters apart. All right. And driven by the same oscillator. So that means the sound coming out from these two speakers are identical. A listener is originally at point O. So this means right located 8 meters from the center. So this means the O point is at the center right in between these two speakers. Now the listener then walks to point P, which is a perpendicular distance, which is fine. Just go straight up from point O, and the distance was 0.35 before reaching the first minimum in sound intensity. What is the frequency of this oscillator? You want to give it a shot? All right, think carefully. If you're standing at point O, what happened? Of course, the sound that coming out from those two speakers. Okay, let me do this like purposely. I really want to try this, right? Even though it's not exactly the same, but let's assume. That's the wrong one. Sorry, I want to go straight to the center first. So sort of like here, one. Assuming that it takes 3 wavelengths to reach point O, let's assume that. Because O is perfectly at the center, so that means the wave from the bottom speaker will take exactly the same distance to reach point O as well. Does that make sense to you guys? So that means while you're standing at the center between these two speakers, the wave that coming from those two sources will travel at the same distance already. So that means at O, delta R is, okay, let me write R1 minus R2, is 0. And we knew that by having this mean the phi must be 0 as well. So saying in like a very official way is the path difference is 0. So the phase difference is 0. So what you are getting is going to be a constructive interference. Does that make sense? Cool. So that means you're going to hear a loud sound. The sound will be, I mean, you know that when it's in a perfect constructive interference, the amplitude will be twice as big. So it means you're going to hear a loud sound at point O. But now you walk away from point O. So once you keep walking, the distance travels by those two waves now is going to be different. You start to get delta R to be non-zero. Does that make sense? But it's still not perfectly cancel. You just have to keep walking until you reach point P. The information say you reaches the first minimum. What does it mean? It means going from O to P, you start from the loudest at O, go to the 0 amplitude at P. You know from this information or the clue that at point P, the delta R must be what? Must be what? The travel's distance from the two waves must be perfectly equal to half a cycle. You guys with me? Lambda over 2. That is your first lowest intensity, which is nothing. It's quiet sound, no sound. And that means the phi, if you want to talk in terms of the phase, is going to be exactly at pi. Cool? So what do we need is just, that's it. So all you have to do is just do the calculation then. So all you need is just calculate the distance R1 and R2. R1 and R2. That's what you need to do. Whoa, what did I do? Guys, give me a second here. Is it back? Oh, it's so technical error. Oh, it's still here. Okay, thank you very much. All right, here we go. So what you have to actually need to do is just calculate the R1 here and the R2 right there. That's all you need to do. Just calculate two distance and do the difference. And once you have that difference, you are done. All right, so let's try that. So let me get rid of this. All right, so what I'm going to do is, I missed this one. Okay, let me rewrite this one more time. For point P to have a perfect cancellation the first time, the delta R must be half the cycle, or if you speak in terms of the phase, it's going to be pi. All right, let me write this in like this is a destructive interference. Cool. All right, so what you need to figure out is just R1 and R2, which can be done very easily in the sense that to figure R1, you need this triangle over here. Now that's going to be a number crunching a little bit here, but that is a right triangle that you will be able to calculate R1. So R1 is just going to be, what's going on here? So many problems today. R1 is equal to square root, all right? Look at the upper triangle over there, is going to be 1.15 square plus 8 square. Cool? And for the R2, you take a look at the bottom triangle over here. Right there. Okay, so R2 will be just square root of 1.85 square plus 8 square. Cool? All right, it's not very colorful today. All right, and once you have those two, that's it. You just say, because now we know that R2 is bigger than R1, so we just say take R2 minus R1 and equate that to lambda over 2. All right, once you have that, it means you're going to be able to figure out the lambda. So the frequency is just going to be, I don't know why I cannot write at that spot. Something is wrong. Okay, R2 minus R1 is equal to lambda over 2. So F equal to V over lambda. And you are done.
Okay.
Oh, what a day. What a day. All right. You guys with me? Thank you for your patience here. I'm just writing on my phone right now. I forgot my tablet. Okay. All right. So over here, I hope you see the way to treat this one in either the phase angle. I mean, in terms of like, if you want to speak in terms of the angle, or you would like to do it in terms of the distance. All right. And this one, the reason I say this can be actually done if we were to meet in class, I can actually show you this experiment. Assuming that in front of our class, there should have like 2 speakers. And what I can do is just, I'm going to hook it up onto my phone and just have my phone generate a single frequency out. And for those students that sit right in the middle of those 2 speakers, will hear a louder sound. But then the thing is, for those of you that sit just in the position that you get a destructive interference, will hear a quiet sound. Or you can just walk around and you will hear that there is a variation of the sound intensity that you can perceive in your ear. All right, so maybe you can starting in the center of the class, and then you move your head a little bit to the side, then the intensity will drop and then go quiet, and it will just go turn back up loud again and quiet again. So that means if you keep walking, you can go up and it will just loud again, because now you hit the condition of R1 minus R2 or R2 minus R1, the path difference equal to 1 wavelength. You guys with me here?
Okay.
And if you keep walking, it will become quiet again because you hit the next destructive interference when the path difference is 3 lambda and a half. And if you keep walking up, it will go loud again because the path difference is now 2 lambda. And if you keep going up, it will be quiet again because you're going to the next destructive interference, on and on and on. Okay? So that means if you walk around, there will be a pattern of the positions where the sound is loud and the sound is quiet due to the structure of this path difference or the interference effects. That's all. Sounds good? All right, guys. And that is it for the interference topics here. Any questions? I hope you guys still okay with my writing here. All right. Trying to do my best over here. All right, guys. So if no questions, let's take a break right here. And after the break, I have one more stuff for you to play around with this interference. Okay. And it's going to be a lot of fun. Okay. All right. And if you really want to love, oh, actually, I have a bigger picture over here. I should have used this one instead. All right. This is a zoom in if you really want to do like an, trigonometric and all this stuff, Pythagorean theorem and everything. So it's just on this one here. Cool. All right, guys. So take a break right here. I'll see you guys in 10 minutes. Okay. All right, guys. So I have a next question for you. What if the wave that we have, instead of traveling in the same direction as you saw before, it turns out to travel in the opposite direction instead? What do you think it will happen? That's it. That's my only question I have left for you today. But the answer might take like 30 minutes. All right. What do you think? So what we are going to try to do together here is this, guys. So let's write down the wave function one more time, such to practice as well, and just to meet our requirements over here. So what I'm going to show you is this. Let me call it the y1, just like what we have before. And now it's the same amplitude. So let me call it A. And it's a sine kx, no problem. Let's have this one traveling to the right direction. So I put the negative sign there, omega t. And because I don't care about the starting point or starting phase, I don't care. So I set that phi to 0. That's it. This is good. This is a right traveling wave, correct? Now I said I need another wave that look exactly like this, but traveling to your left. What would that be? บอกอาจารย์บอก the only thing that อาจารย์ need is just taking the exact same form of everything, except you pick positive sign instead. Does that make sense? Okay?
Okay.
All right, so with that, now I want these two waves to meet. I want these two waves to meet. The net wave is just by superposition principle, sorry. It's just y1 plus y2. Can you give, I think you forget to open the camera. Oh, okay. I just want to hide behind my microphone here. Sorry, my bad. All right. So what you need is just to add them together. Here we go, guys. Give me the wave function of the combined wave. Woo! All right. So what do you think? Well, Ajahn, don't have to think anything. Just apply the trigonometric formula that you just did. What else can we do? All right, guys. So we're going to go through this one together, shall we? So it's going to be equal to 2a. Yeah, because there's a factor of 2. I pull a common factor a out. Now, I'm going to slowly do this one. I don't want to confuse you guys anymore. So it's a cosine. Take the difference divided by 2. Okay? The reason I say the difference because I don't care much. Cosine of positive or negative are exactly the same. So I can just take the first bracket, in the first argument here, subtract out the second argument. So what you can see is when you take the difference, the kx term disappear. You guys with me? When you take the difference, the kx term disappear. You are left with just the omega term. So you have negative omega t minus omega t. So I take the front, subtracting out the back, divided by 2. Oh, where is my undo? Okay, anyway, looks not too bad. So let's keep it there. Oh, really sorry for the problems not having the device with me here. Okay, so that's it. Oh, that now here it is. Dang, it's too far. There you go. All right, divided by 2. Okay. All right, that's the first term. That's done. What about the sine term? The sine term will be the sum divided by 2. When you sum these two arguments, the negative omega t and the omega t will cancel. You will be left with just the kx. So it's going to be kx plus kx over 2. Cool? Very nice. Okay. That icon suggestion keep popping up. Can I grab one just for fun? Will that work? Oh shoot. That's not good. That's not what I intended. Oh my god. I should have done that. Oh shoot. Sorry guys. Just play it midnight. Okay, very good. All right, now let me rearrange this final form to make it sort of like nice and neat one more time. So it looked like this: 2a cosine. Now I don't care, it's a negative omega t or positive omega t, they look the same. So just take omega t sine kx. What do you see? Yeah, I know, I'm writing on the phone, yes. That's why there was something popping up. There's an SMS message coming. Sorry, I forgot my tablet at my office, and then I just realized this morning I couldn't grab anything, so I have to write it on my... The good thing is still I can still write on my phone, otherwise it will be even worse if I have to use the mouse or anything. Okay, so what do you see, guys? You see 2a cosine omega t and multiply by the sine kx. But this is a weird looking, because it seems like the features that we learned before, like the kx plus or minus omega t, seems to disappear. Even though it disappeared, it's still a wave anyway, because I mean, if you break this thing out and rewrite it in terms of the summation of the two waves, it still have the kx minus omega t and kx plus omega t in it. But once you combine them, after the combination, it has this form of the function. So I just want to ask you, what do you see from this function? It's still two variable function anyway, right? So what you have over here is just like, oh, Ajahn, there's a t, there's an x in there, but now they are not in the same terms anymore. But what can you tell me about this one? Slowly think about this, Ajahn. If you look at this, and just for fun, Bojan, you are seeing this kx term. And if, I mean, we do this all the time, Bojan, at x equal to 0. At x equal to 0, how come your wave function go to 0? Because, I mean, it's a sine 0. So what does it mean? It means at this position of x equal to 0, this medium, the element inside the medium at this position, will not move. Wow! Does that make sense? Okay, come again. Think about it carefully. At x equal to 0, your y is always 0 no matter what time, because I mean it's 0 at all time. So that means at this position you don't have any oscillation anymore in the medium. Does that make sense? Okay, one more time. If I said x equal to whatever that makes my kx equal to 2 pi. So let me do this. If kx equal to 2 pi, you also get y equal to 0. Cool? One more time. If you take kx to be equal to 4 pi, y is equal to 0 as well. But wait a second, Ajahn. The sine function go to 0 no matter it's 2 pi, 4 pi, or it's even half of the 2 pi, which is pi. So that means if the kx equal to, okay, let me write it on top here. If kx is equal to pi, y is already equal to 0. 3 pi is already equal to 0. On and on and on. You start to see the progression of what I'm doing over here. See this? So what I'm saying over here is, it looks like at some particular value of x, you won't get any oscillation from the medium whatsoever. And if I want, I can calculate for you exactly where x equal to 0 is there, x equal to 2 pi over k, x equal to 4 pi over k, on and on. But if I do carefully, look at this. K, okay, let me pull this one out. Kx equal to pi, okay, that means 2 pi over lambda x is equal to pi. Pi cancel. So that means x is lambda over 2. Whoa. So that means at x equal to 0, nothing moves. At x equal to lambda over 2, nothing moves. I can keep going. I can do this kx equal to 2 pi. Something is bad going on here. Oh my God. All right, but anyway, let me summarize here, guys. Sorry, today it's really bad. I don't know how to, I know how to turn this thing off. I just, not now. So what you have over here is, it means at x equal to 0, lambda over 2, lambda over 3. I'm sorry, not lambda over t. It's going to be at x equal to 0, at equal to lambda over 2, at lambda, 3 lambda over 2, 2 lambda, on and on and on, will be y equal to 0. This is a summary of what we have done right now. You guys with me here? So what you have at this point is saying that by having two waves going in the opposite direction, after the combination, it appears that there are some position on this wave will not oscillate anymore. And those positions are at 0, at half the wavelength, at 1 wavelength, at 3.5 wavelength, on and on and on. So every half of the wavelength, you get no movement. And hence the name. Here we go, guys. All right, it doesn't have to be that big. It's called standing waves, because there are some points on the wave is just keep standing, not moving whatsoever. Isn't that nice? And of course, the rest will start to oscillate a little bit, up and down, up and down, up and down. However, what you have over here is just like, okay, all you have to do is just plug in other value of x's, and everything's still oscillating up and down, but at a different value. Okay, so that means there will be some points in between that eventually the oscillation will appear the maximum. All right, and that will be the halfway in between the point that you are seeing over here. So if you look carefully on this one, I'll explain more on what this is. So you see that there will be a point on the wave that does not move, and that's the point indicated by the N symbol over there. That's exactly what I have. Or this one here. N, and as you can see, you have this N position over here, just somewhere in between the wavelength. Okay, if you look further, it may be a little bit clearer. This is a point where there's no movement, no movement, no movement. So we call these points that's no displacement whatsoever at any time to be node. We call this node. Okay. And if you look here, if you start the wave here, every time you complete one full cycle, that is one perfect lambda, yes? Okay? So as you can see, if you break this thing in half, that's half the wavelength. So as you can see, the distance between node to node, that's exactly half the wavelength as we already discussed on the right. We say that the position that does not have any displacement will be separated by half a wavelength, half a wavelength, half a wavelength. Cool? Okay, so this is standing wave. Conclusion, you get a standing wave whenever you have two waves that looks identical but traveling in the opposite direction. Opposite direction. You're going to get the standing wave. Now, here comes I would say the confusion might start to come in. But Ajahn, what is this figure over here? That doesn't make sense. because you have only single wave. How come it's split in half and then start to show up like a loop? Okay, so we'll have the explanation for the loop, explain the way that you describe the standing wave using a loop by going here, guys. So another website that I want you to try today is going to allphysics.com. Everyone try this. Okay, and I'm gonna go there with you guys as well. And it's gonna be a lot of fun today because you have to understand this one first. Otherwise, I mean, in the past, I can talk to you about the mathematics and everything, but then at the end, you don't even know what the standing wave is about. So what I'm gonna do is I'm gonna share the screen here. Moving on. All right, and I'm gonna go to my website, which is right here. Where is that? Here we go. There you go. All right, you guys seeing this? Okay, so that's at allphysics.com. All right, and okay, let me split this one out. I can move it here. Is that with me now? No. No, nothing works today. Meeting control. What is going on here? Okay, let me do it one more time, guys. Oh, it has to be window sharing. Here we go. Share. All right, better. Okay, so what you have over here is now you can go to waves. All right, and once again, I still encourage you guys to try to play around with this another website that has a very good simulations over here, and we can play a lot with this, talking about the superposition over here. So, but for our purpose right now, let's move on and move to standing waves here, guys. Okay, so here, bam. All right, so this is the concept of the standing wave. So in reality, what you have here is just single waves. There's no way that you're gonna get two waves, of course. All right, but in general, if you think of this one and it's oscillate up and down, and it's going super quick, you start to be able to see that it's gonna look like a loop. Does that make sense? So this is showcasing the case of the standing wave on a string. So let me turn it onto, I think that I can click on this one, air column, and close in, and oh, what is going on? All right, I think I have to refresh, I guess. I don't know what is going on with this one. Okay, but this is not a good one yet. So this is a standing wave on a string. So let's go to this. I want you to see at this one, air column resonance. This is the one. This is going to be close to what we have. All right, and this is exactly the shape of the column of the air that is that shows in the handout. I can pick the open in both ends first for now. So this means now the air column here is just think of it like a pipe. Okay, so it's like a tube with two open ends. And now I'm just going to start by showing the original wave. This is what it looks like. Okay, so this means you send in the sound waves. And this, even though it doesn't show up as a longitudinal wave here, but that's the mathematical description of where the displacement of the air in this column are. But the idea is this is the typical waves that you can describe the sound wave in this air column. Now I want this to travel, so I'm gonna start running this. Okay, and as you can see, this is, I just say show the original wave. So I'm just sending in the wave, and it seems that Ajahn, this is fine. This is just like the previous simulation that we did before. You send in a wave and the wave just travel through the open window on the right and you're done, right? But it turns out the waves will exhibit a property that it gets reflection every time that it changes the medium. Okay, come again, one more time. Okay?
Okay.
So waves, every time that it hits some changes, it it experience some changes, there will be a portion of the wave get reflected all the time. And this is the reason why we're going to learn about this as well in light, in optics. If you look at your glass windows, even though the windows is transparent, right? But as you can see, no matter how you polish your windows, you always see yourself, your reflection of yourself, a little bit, like a faint reflection of you. See? So this means even though the window is perfectly clear, but there's no way that you cannot see yourself in there. There will be a little bit of reflection going on all the time. And that is because the light wave has to go through from air, get to the glass, and get out from the air. So every time that the light changes the medium, part of it will get reflected. Same thing over here, guys. The air inside the column and the air outside the column can be considered to be different type of medium because the way that air oscillates in the tube and outside the tube are different. So that means when the sound is being sent into these columns, even though it looks like it's going to come out to the right hand side, right? Just like nothing happens. But it turns out if I click show the show the first reflected wave, there will be a little bit of that sound get reflected back. You see what I'm going at here right now? And now when that orange curve that get reflected back hit the left open end, it will get reflected back into the tube again. So I can show the second reflection here. See, and that is the dash blue line right there. And that dash blue waves that get from the second reflection hit the right side of this open tube again. It will have a portion of it get reflected back again. Crazy, yeah? Oh, no need to clap there. So actually, this simulation is very neat because they include up to 5th reflection. And this is crazy going on, which cannot be seen in the textbook. And I think many of the textbook actually give you a wrong impression that you only get like just a first reflection and then you're done. But no, it actually is a multiple reflection that is going on inside the tube. Okay? What we care about is the end effect of this. What is going to be the grand summary of this? So what we are going to show you is show their sum. See, look at the green. All right, I think we can reduce this one down a little bit so it doesn't slow down the simulation much. So the green is your summation, okay? And if I have to show all of that summation, now you get crazy summation here, right? So you have to sum all those reflection, double reflection, triple reflections, and on until the bottom tube there show you the sum of all waves and pretty much all of those sums again. You stay with me right now? So what I'm saying over here is by sending a sound into a tube, you get multiple reflection. So by the superposition principle, the net final waves come from the summation of all waves. And that's it. The all summations shows you in the bottom curve right there. So I think now I can turn this thing off right now. Okay, here we go. So after all those reflection that it goes on in here, okay, let me reduce down into just the first two. Then the bottom curve, the bottom figure over here showcase the net result. And can you see this? It doesn't give you anything much. No. Okay, so this is not a lot. So you can expect that when you send in the sound will be pretty quiet from this outcome. That's not much of sound. So what can you change, Ba'ajan? How can you do, or what things can be done? So the thing that you can do is this. I can change the air column here. And let it go again. Bam. Can you see this? Look at the bottom. Don't forget, the upper one is like a, multiple reflection going on, summing, everything go crazy. But at the end, the resultant wave is the bottom. Okay, so I think just to make simulation run a little bit faster here, you see? So look at the bottom one. It's oscillate up and down very huge in comparison to the previous length. And if I adjust the length one more time, there will be some length that doesn't seem to work. This is not a good length. Right? Not good. Okay. On the other hand, instead of changing the length of the tube, which is sort of hard to do, I can just fix the length. Okay, let me go back to 5 meter length of the tube. But then I can adjust the wavelength instead. See that? I can change the wavelength. So let me match the wavelength to be at 5, exactly the same size, and let it run and see what it goes. Isn't it cool? Whoa. All right, it's a good big oscillation at the end. It seems like it's nice. So 5 meter wavelength seems to match with the 5 meter tube. So let me try different wavelength by reduce it down. And let me try again. So let me do 4.4. I'm just going crazy here. Just pick any number. See, the oscillation is not as great anymore. It's pretty bad. Okay, so let me tune it down again. Go crazy and try. Not good. Still not good. So I think I'm gonna try to pick something that's sort of matched with the number 5. So I'm then gonna go 2.5. If I can go there. Yep. All right, pretty close. 2.5. Run. Whoa. All right, to be perfect, let me type it in. 2.5. There you go. Run. See, it come up and oscillate a lot again. See that? Okay, isn't it fun? I don't know, I'm having fun alone or what? I mean, you guys still with me, yeah? Right? Okay. So what I'm seeing over here is just like, hey, there are only some wavelength that can give you the big sum at the end. And there will be some wavelength that doesn't give you a lot. Okay? And that we call this particular wavelength that you pick or particular frequency that you pick to send into this tube that give off the big summation at the end to be the resonance phenomena. Isn't that cool? Woo! It's huge. Okay. All right. So that's called resonance. And this is the reason why when you have a tube and then you try to generate a sound out of the tube, and the easiest tube is just this straw from coffee cup over here. If you blow on it, I don't know you hear this or not. You only hear a sound coming out of it at a single frequency. That's the dominant one. The majority of the sound coming out, it will be dominated by one single frequency, not a lot of frequency or a mix of frequency. And that is the reason why you only hear that majority of one big frequency to be the main sound that you hear from that blowing of the tube, is because it matches the resonance condition over here. อันนี้อาจารย์พูดรู้เรื่องไหมวะ I don't know, but this is it sounds simple, but behind the scene is pretty complicated. Mechanism over here. And as you can see, the only way that you can change the sound coming out of it is just, now you already saw it. I might just have to change the tube size. I have to change the length. And once I change the length, it will change the frequency that can fit in there. That will give you the big sum at the end. นี่พอรู้เรื่องไหมวะ All right, so I hope by combining these two together, and I think it will be nice if you can come back and play with this a little bit more, then you will be able to understand what we are trying to do here. All right, so let me stop and go back to my screen over here. So what you have over here is now, I hope that by come back and look at this figure again, you start to see that, oh, John, I have a tube with the fixed length L, and I just want to know what kind of condition that will give me the big summation of the wave at the end, or what would be the resonance effect, or there's so many or here, or how can I generate a standing wave that fits perfectly inside this tube. I want the perfect fit for me to get a very nice sort of like outcome of the superposition of all those waves. You guys with me here? So this is what I'm going to try to show you together. So I'm going to add one more page here. And let's do this together. It would be nice. Okay, so this is how it's supposed to be done. So now you have a fixed length of a tube, right? And because this tube is an open end tube, so you assume, or at least it's a very good guess, that the air at the ends of the tubes can pretty much move very freely. So that means you can assume that this is supposed to be the place where the amplitude is going to be big. We're going to call this antinode. Antinode. So as the name implies, is opposite to the node. The node is the place where the oscillation is zero, but the antinode is the place where the oscillation is the biggest. But we can understand from the sinusoidal waves, the position where it's going to oscillate the biggest is going to be exactly halfway between the nodes, because that's how the sinusoidal and cosine function are constructed. So that means in between these two, that's where the node is going to be placed. Okay? And not only that, we also know that the distance between the node is half of the wavelength, right? We already saw that from this one. So from node to node is half the wavelength. Node to node is half the wavelength. So antinode to antinode is supposed to be half the wavelength as well. Or if you prefer, from the antinode to node is going to be lambda over 4. Cool? Lambda over 4. So now the game begins. The only thing that you need to generate a standing wave that fits into this, you just have to make sure that you fit the wave that looks just like this. Just like this means the antinode is on the left, antinode is on the right, and the node is in between. So this is a reason why, to showcase this possibility here, all I'm doing is just, okay, let me change the color here a little bit. All I am doing is just fit the wave inside this tube that fit this condition over here. So what I can do is this, well, Ajahn, let's do this. Here we go. Does that make sense? I don't know does that make sense or not, but the idea is this. I would like to draw something that can showcase that there is a place where there's no oscillation whatsoever, which is at position N. And between those ends will be the place where the oscillation is the biggest. So we're going to utilize the idea that the wave is actually oscillate up and down, up and down, up and down, but it's very quickly. So that's why what I can do is just, I can just write those waves up and down quickly, and it looks like a loop. And the position where the loop, the wave just cut itself, and at the center like this one, that is the place where there's no displacement, there's no oscillation. Does that make sense? Or this is a very, I don't know, am I explaining it correctly? Or maybe not correctly, but it's just like explaining this to you and allow you to make connections or not. Okay, one more time. Let me do this. Another way that you can do this, Ajahn, all right, the condition that you need is you want the open end to be antinode and antinode. And now you fit one node in between. But Ajahn, what if I can do a little bit better? Saying that all you need is antinode at the ends. But what if I want to fit two nodes in between? Can we do it? Well, yeah, and of course you can do it. So you just fit two nodes in there. So I just do one more twist. Oh, that's not good. Okay, I just do one more twist to it, as long as I keep both ends to be antinode. So that means I just do this. Back to antinode. Back to antinode. You guys with me here? So with this, I have two nodes showing up here, and another node showing up here. So that means in between of this one, gonna have another antinode in between. So it's like playing games over here. That, well, Ajahn, if I can do one more, would it be okay? Well, yeah. As long as you keep both ends to be antinode, you can, do one more. There you go. Yeah, that works. Because you start from antinode on the left end and antinode on the right end, but now you squeeze in 3 nodes in between. So this means you can keep doing on and on and on, as long as you keep the conditions at the ends to be exactly what we need. And from there, you can answer about what should be the wavelength that give you each condition. So the second case, probably the easiest way to think. Look at this, guys. The wave starting from here, go down and go up, come back to the original position. See that? So that means what you're seeing over here, this is exactly one wavelength. With me? Okay, one more time. Look at this one on the right. If I start here, go down, come back up, back to the original position, that is my one wavelength. See that? Okay. And if you go back to the original, the easiest one here, you start from here, go down. It's still not going that far because you need another half to go back to the original. So what you're seeing over here, this is your half a wavelength. With me now? So from the look of this one, so that means you can link between the wavelength that you want to fit into the tube and the length of the tube itself. So look at the first case on the upper left. Because the whole length of the tube is lambda over 2. So in this particular case, you will see that length of the tube is lambda over 2. Or you say that your wavelength that you fit in there is twice the length of the tube. Cool? If you look at this case over here, but oh, John, I can see it. The length of the tube is exactly wavelength. So no need to do anything anymore. But over here, but oh, John, I can see it. It's one wavelength and a half. See, this is another extra half. But oh, it's gonna be 3 wavelength over 2, which is equal to the length of the tube. You guys with me? So from this case, your wavelength is 2L over lambda. There you go. And you can keep doing this on and on and on. So if you try to sort of like draw this one in a pattern, so you can summarize that lambda in the second case is 2L over 2. Oh, I shouldn't have any lambda here, guys. Sorry. 2L over 3, not 2L over lambda. There you go. All right, so now you can see the progression of what is going on. The easiest case, your wavelength is twice the length, 2L. The second one, the wavelength is 2L over 2. The third case is 2L over 3. And now you start to be able to see the pattern. If you want to fit in the higher frequency wave in it, it's going to be lambda equal to 2L over 4, 2L over 5, 2L over 6, on and on. And that, go back to this slide. I hope you see how to read this one now. See, the case on the upper one, you say lambda is twice the length of the tube. So the frequency is just V over lambda, and then you can figure out what should be the frequency you fit in the first case. Second one here, I know that now the wavelength is just the length of the tube. So the frequency is just V over wavelength, and this V over L, that is the frequency of the second case. On and on, you just keep doing it. The third case over here, the lambda is 2L over 3. So the frequency can be flipped over, and you can calculate what should be the frequency in the third case, fourth case, fifth case, on and on. And this is how you generate standing waves in an air column. Very cool.
Okay.
All right, and now I hope by showing you the simulation, you can see that why other frequencies or other wavelengths doesn't show up as something that you can hear easily from those two, because it doesn't fit this condition. So the amplitude of the net wave or the resultant wave is so small. You're going to hear the sound coming out from the tube from the one that has the largest amplitude of oscillation, which is all these standing waves conditions here. งงไหมเนี่ย But at the end, after the complicated, well, not too complicated, but it just after summing all these opposite direction waves that going in the opposite, the wave that look exactly the same but point or travel in the opposite direction, you get the form of the standing wave. But the process that you need to do at the end is just pick the right wavelength to fit into your tube that meet the conditions at the ends. And once you know the conditions at the end, in this case, you need both antinode, because at open ends, you allow air to move freely. So that will be the place where the oscillation can happen the biggest. So you set your two ends to be antinode, and the rest you just fit the nodes in between, as many as you want. Does that make sense? If this kind of makes sense, let me do one more here. What if the tube is one open and one end? So now the game is kind of fun because, okay, then the open end will be the antinode, and the closed end over here, because it's already a wall, so the air there cannot move, so you can assign the nodes to that wall. Does that make sense? So now the rest is just fit the wave that meet this condition of antinode on one side and node on the other side. The easiest shape that you can get is the first one. You go straight from antinode to node. That's it. That's probably the easiest one to get. But then you can do one more twist. But as long as the left is an antinode, the right is a node, I can fit extra node in between. I do one more twist. That's good. You get a second conditions that meet the criteria. And you can do extra twist if you want, keeping the left to be the antinode, the right to be the node, and then you get the third case. On and on and on. And now with the knowledge that we saw before, let me ask you about, hey guys, can you give me the wavelength on each case? Can you?
Okay.
Well done, no problem. Look at the first case. It's an antinode to the node. If you draw curve over here, oh done, this is not even half of the wavelength. It's just a quarter of a wavelength. So over here you say a quarter of a wavelength equal to the length of the tube, or that means the lambda is just 4 times the length. See right there. Cool. And once you know the wavelength, you can calculate the velocity of the frequency of this case. Oh, what is going on here? By doing F equal to V over lambda, and that is just V over 4L, and that is it. You're done.
Okay.
Okay, what about the second case? Well, Ajahn, that's not bad. When you look at this one, this is wave that half is right here, and it's half and a quarter. So that means it's a 3/4 of a wave, equal to the length of the tube. With me? So that means from here, the lambda is just going to be 4L over 3. And from here, you can figure out what should be the frequency. And it's just V over 4L. And then I flip 3 to the top. Right there. Cool. And you can keep going now. You can guess. This one is going to be 5 over 4 lambda. Right? Because you have one complete loop and a quarter right there. It's a complete loop and a quarter. So it's going to be 5/4 lambda equal to the length of the tube. So the lambda is 4L over 5. So frequency is going to be 5V over 4L. And now you start to see the sequence. What you get is, oh, the next one must be 7, must be 9, must be 11. So it's going to be odd multiple of lambda over 4 equal to the length of the tube. And from here, you can calculate the frequency. And that's it. You are done.
Okay.
Okay? All right. So I don't know. This one, it always takes me a lot of time to explain, but I don't know, did I do a good job of explaining or make connections with the sinusoidal waves, the wave traveling in the opposite direction, and try to have the way to describe the standing waves phenomena well or not today, because I know it just my writing is bad here. It's only single color. Really sorry about this, but I hope you get some connections here. So I don't want to push too much, because I think because of my crypto device over here, then I will leave it here. And I think I will explain this one more time, right? Just sort of like go back and explain a little bit better with maybe sort of like do another round of summarize the whole thing here before I show you how to calculate the exercises. Sounds like a good plan? All right, because otherwise then it might be just too confusing to push this thing further. All right, guys, so I think I'm gonna stop right here, and I hope have it sit in your head a little bit, and when I see each other next time, I will just show you how to apply this to a real problems and maybe some demonstration of what that you can notice from everyday lives experiences and all this stuff. Sounds good? All right, guys, thank you for today, and that is it. All right.